The planet you're lying on keeps time in a unit you've never once used. Not the second, not the year, the million years. That's the rate at which it does almost everything. Opens an ocean, lifts a mountain range, and wears it back down to sand. Lets the ice come south, and then, unhurried, calls it home again. For nearly all of its long biography, the Earth has moved too slowly for anything alive to feel it moving at all. The light dims and returns across thousands of years. The cold settles in like a season that has forgotten how to end. Whatever clock you live by, the day, the heartbeat, the held breath, it was never built to register a planet's ordinary pace, and the planet, for its part, has seldom done anything quickly enough for a creature like you to notice. And then once, only once, in the whole history of animals with backbones and eyes and the first faint beginnings of a brain, like the one you're using now, it did something at a speed you could count on the fingers of one hand. Not a million years, not 1,000, not even an afternoon. About 10 seconds. One slow breath, drawn and let go. This was 66 million years ago, on an ordinary afternoon, over a warm and shallow sea. Something close to the size of a mountain came down through the sky and touched the planet, and in the time it would take you to count slowly to 10, the shape of every life that would ever follow, including eventually yours, was decided, not influenced. Decided. The 10 seconds didn't begin a long argument the planet would go on having with itself for ages afterward. They ended one. Everything that has lived since, every animal you've ever seen or feared or eaten, and the animal you happen to be, descends from the handful of small things that came through those seconds and the long dark behind them. Because a dark did come after. Not a night, a winter measured in years, the sun shut out behind a sky that had been thrown up off the ground, the world cooled and dimmed and quieted, until most of what had been alive on it was not. You're here, listening to this, because on that ordinary afternoon, something small and unremarkable happened to be underground, and stayed there, and outlasted the worst of it. For almost all of the time human beings have known this happened, they couldn't say what those 10 seconds were actually like, only that the rock had kept them, the same thin record on every continent, and that something enormous had passed through. That has changed. We can move through those seconds now, almost one at a time, slowly, the way you'd take a watch apart to see what each small piece was doing in the instant the whole thing stopped. That's the strange part. The fastest, most violent thing that ever happened to the living surface of this planet is also now one of the few we can hold still and look at closely. If a quiet thing like this seems worth making, subscribing is the single most useful thing you can do for it. And there's a question worth leaving in the comments if you're willing. When you picture those 10 seconds, the speed of them, a mountain meeting the ground in less time than it takes to draw a breath, does that frighten you? Or is there something almost steadying in how quickly the planet moved and how long ago it was? It's a more interesting question than almost any fact in this field, and the answers are worth reading. So settle in. The lamp near you is probably a little brighter than it needs to be, and the day you've had is probably still sitting somewhere in your shoulders. Let it. The afternoon we're going back to was, by every sign available to anything standing in it, entirely unremarkable. A warm coast, a high sun, a sea doing what it had done without interruption for millions of years. And somewhere overhead, still soundless, still no more than a faint point of light against the blue, the thing that would end it was already most of the way here. Come down out of that empty sky, then, to the water it was falling toward. It was a shallow sea, the kind that lies over the drowned edge of a continent rather than the deep of an open ocean, warm all the way to the bottom, clear enough that the light reached the sand, scattered with low reefs that clams had been building there, layer on layer, for millions of years. This was the shelf that is now the Yucatan in Mexico, though in those days it lay under open tropical water with no coastline anyone alive today would know. Coiled shelled animals the size of dinner plates drifted above the reefs, ammonites, distant cousins of the squid and the octopus, carrying ribbed shells curled like ram's horns. Bigger things moved in the blue below them, including the long sea lizards we call mosasaurs, the great hunters of that sea. The afternoon was hot and humid and completely uneventful, and it had every reason in the world to expect to be followed by another one exactly like it. If you had been standing in it, up to your knees in that warm, shallow water, the sun pressing on the back of your neck, you would have seen nothing wrong, because there was nothing wrong to see. The sky was the plain blue of a hot day, give or take a single point of light too faint and too high to bother with, the sort of thing the eye slides past without ever quite deciding it was there. Nothing in the water knew, nothing on the nearest land, a few 100 kilometers off, and there was land with animals on it, the last generation of a kind that had walked the earth for 150 million years, knew either. The planet did not know, in whatever sense a planet can be said to know things. The rock that would one day record this afternoon in perfect detail, the rock that has kept it for us, could not yet tell it apart from the afternoon before. That point of light was a single piece of stone about 10 kilometers across, maybe a little more. The people who measure it now disagree over the last few kilometers, the way you'd disagree about the size of something glimpsed once and never seen again. Call it the size of a mountain, as long as you remember that no mountain has ever behaved like this. It was dark, and it was very old. A carbon-rich body left over from the making of the planets, from somewhere beyond the orbits of the giant worlds, older than any living thing that had ever existed on Earth. For a long time, the story cast it as a comet, a bright wanderer from the cold outer dark. The chemistry it left behind has since pointed somewhere quieter, a dim, unhurried asteroid that had found its way onto a path ending at that warm sea and was now in the final seconds of the fall. It was also moving faster than almost anything in your experience can prepare you for, and it arrived ahead of its own sound. Sound crawls. This did not. By the time any noise it made could have reached the surface, the thing making the noise was already there. So the first announcement of it, had there been anyone to receive one, would not have been a roar, but a light. The air directly in front of it, compressed and unable to escape, flaring white-hot, a small false sun switched on in the afternoon sky and growing. We tend to think of the sky as a kind of shield, and most of the time we're right. Every night the Earth runs into thousands of tons of rock and dust, and the air turns nearly all of it into nothing. A speck no bigger than a grain of sand becomes a streak of light you'd make a wish on. A boulder becomes a fireball that breaks into cinders long before it reaches the ground. The atmosphere is very good at this, and has been doing it for as long as there's been a surface underneath to protect. But everything it does by heat and friction against the air itself, and that kind of defense has an upper limit, and a mountain is far past it. There was simply not enough air in the way. 100 kilometers of atmosphere sounds like a real thickness until something 10 kilometers wide is falling through it at 20 kilometers a second. The entire vertical depth of the sky crossed in about the time it takes to let out one slow breath. The air ahead of it couldn't move aside fast enough to matter. It was crushed and flung and lit, and it slowed the asteroid by next to nothing. Whatever the sky is for, it was not for this. To something that large, moving that fast, the planet had no atmosphere worth the name. And there's one more thing about that ordinary day worth holding on to, because it will come to matter more than almost anything else: the rock under the shallow sea. Most of the planet's surface, hit by something like this, answers in rock, shattered, melted, thrown, but ordinary rock. The floor of the Yucatan Shelf was not ordinary. It was built from the leavings of the sea itself, thick beds of limestone, the pressed-down remains of old reefs and shells, and threaded all through them, nearly as thick, beds of gypsum, the pale rock that forms where a shallow sea dries down and leaves its salts behind. Limestone is carbon, locked in stone. Gypsum is sulfur, locked in stone. Of every place on Earth a mountain could have come down, this was close to the worst, a seabed that, heated hard enough, wouldn't only break, but breathe out, and put into the sky the two substances best at darkening it. None of that had happened yet. For now, the seabed just lay there in the warm, being unremarkable, the way it had been for ages. Most tellings of this begin a heartbeat later than we are now, with the flash and the crater, because that's where the spectacle is. But the honest place to start is here, in the air, in the last second or two before anything has touched, partly because this is the only stretch of the whole story in which the outcome was ever in any doubt, and it stayed in doubt only briefly, and partly because this is the last moment the planet was still the old planet, the Cretaceous one, the one with the reefs and the ammonites and the long, uninterrupted afternoons. What comes after is a different planet. The changeover takes about 10 seconds. The asteroid crossed the last of the air, its leading face, glowing now, dragging a sheath of superheated gas, closed the final few hundred meters toward the bright skin of the sea and the shallow water beneath it, and the limestone and the gypsum and the warm, uneventful world that still had no idea it was there. And then it touched. The Cretaceous, the reefs, the ammonites, the long afternoon of all of it had about half a second left to be anything at all. Touched is the wrong word, really, but it's the only honest place to begin, because for the first instant, nothing happened that the eye would have called a collision at all. The bottom of the asteroid met the surface of the sea and the seabed beneath it, and stopped. The rest of the asteroid did not. The imagination has trouble here, so it's worth holding still. When you stop a falling object, a book set down on a table, a car run into a wall, the whole thing halts more or less together because the news of the collision travels up through it almost instantly compared with how fast it was moving. A push moves through solid rock at something like a few kilometers a second, which is quick, but the asteroid was coming in at 20. The bottom kilometer hit and crumpled and stopped, and the top of the mountain, 9 kilometers above it, had no way of knowing yet. The signal that would have told it to stop was itself only crawling downward through the rock at a few kilometers a second, and the rock above was descending into that signal far faster than it could climb. So the top kept coming, kept driving down into its own ruined underside at 20 kilometers a second for about half a second. That number isn't poetry. It's simply the time it takes a shudder to climb 10 kilometers of rock. The height of the asteroid, divided by the speed at which rock can pass along a push. Half a second is how long the asteroid spent arriving after it had already landed. What filled that half second was the conversion of a moving mountain into a standing wall of pressure. 2 shock waves were born at the point of contact and ran in opposite directions. One downward and outward into the seabed, one upward into the body of the asteroid. Each a front of compression so severe it crushed the rock it passed through into a fraction of the space that rock had filled a moment before. Ahead of those fronts, the rock was still ordinary, still cool, still itself. Behind them, it was something the surface of the Earth had never been. The pressure at the point of contact climbed past anything in the planet's ordinary experience, past the crushing weight at the bottom of the deepest ocean trench, past the pressure kilometers down in the crust, where rock flows like putty given enough time, past, for a flickering instant, the pressure at the very center of the Earth itself, where the entire weight of the world bears down on the core. For that half second, a patch of shallow seabed in what is now Mexico became the hardest squeezed place on the planet, harder than its core, and it was squeezed not across the millions of years the deep Earth takes, but in the span of a single breath. And all the energy the asteroid had been carrying, The motion of a 10-kilometer mountain traveling at 20 kilometers a second had to go somewhere, because energy never simply vanishes when a thing stops. It only changes form. A car against a wall turns its motion into bent metal and noise and a little warmth. The asteroid carried so much motion, packed so tightly, that when it stopped, there was nowhere for the energy to go but into heat, and the heat ran far past anything that merely melts or boils. The temperature at the contact point rose beyond the heat of any furnace ever built, beyond the temperature of the surface of the sun, and several times past that again. At those temperatures, rock doesn't crack or shatter. It loses its argument with physics altogether. It melts, and then it boils, and then it becomes a gas, a vapor of what used to be stone. The asteroid that had crossed the solar system unmade itself in that half-second. It did not crash and lie there in broken pieces. It stopped being a solid object at all, flashing into glowing vapor and molten rock, and it carried a comparable mass of seabed with it, the limestone, the gypsum, all of it boiling away in the same instant. The shallow sea above the impact point was neither obstacle nor shelter. The water flashed to steam and was simply gone, shouldered aside before it could matter, the way the air had been. And at the very rim of the contact, where the squeezed material met open space at a sharp angle, a thin spray of vaporized rock was forced out sideways and flung across the sky, faster even than the asteroid had been falling, the first matter to leave the scene, running out ahead of everything else that was coming. It's fair to ask how anyone could know what half a second looked like 66 million years on, when the half-second in question destroyed its own evidence, vaporized the very rock it happened to. We know it much the way you'd reconstruct a crash from the wreckage and the laws of motion, rather than from having stood and watched. In laboratories, researchers fire small pellets into stone at a few kilometers a second and read, in the ruins, the same signatures written small. In computers, programs built to follow shock waves, the same physics scaled up, run the half-second forward frame by frame and produce a crater of the right size and shape. And the rock kept a few things of its own, grains of quartz carrying a kind of damage that forms only under shock pressures like these, little beads of melted stone, the chemistry of a vaporized seabed flung clear across the world. The half-second is gone, but it left fingerprints, and the fingerprints all tell the same story. In a half-second slowed down enough to watch, there is no sound yet. The sound is still climbing out of the ground, behind the light. There is a brightness with no good name, a column of vaporized stone and metal lifting off the sea, a pressure wave racing out through the seabed faster than the rock around it can crack. And if you feel something strangely calm in the middle of all that violence, many of the people who have given their lives to studying it say they do. It's because nothing about it is uncertain. Every part of it is only physics doing what physics does when you deliver that much energy into that small a space in that little time. It could not have gone any other way. The mountain could not have bounced, could not have cracked and held. Given the speed and the energy, the outcome that happened was the only one on offer. By the time the half-second is up, by the time the top of the asteroid has finally received the news and there is no longer an asteroid to receive it, the irreversible thing is already done. Everything from here on is consequence. What had been a point of contact, a wound a few kilometers across, now holds more energy than the planet around it can possibly keep still. That energy has only one way to go, out and up and down, into the rock and the sea and the sky in every direction at once. The mountain is gone, the half-second is over, and the ground that a moment ago was a quiet seabed in the warm is about to open. And open it did, but not the way ground opens for a shovel or a quarry charge, in cracks and chunks and a settling cloud of dust. It opened the way a pond opens when a stone drops into it. For a stretch of seconds, the solid rock of the Earth's surface stopped behaving like solid rock and began to behave like a liquid, and the place where the asteroid had been became the center of a splash, a real splash, with a rising crown and falling droplets, except that the droplets were blocks of crust, the size of houses and hills, and the crown stood tens of kilometers tall. Where the warm, shallow sea had been, there was now no sea at all. For tens of kilometers in every direction, the water had been thrown back or boiled off, and what lay at the center was a dry, growing pit in the floor of the ocean, its walls running and slumping, glowing from the heat still pouring out of the broken rock. Rock flows like that only when the forces working on it run so far past its strength that its strength stops counting for anything. A boulder is hard. Lean on it, and it holds. Strike it with a hammer, and it chips. But push on it with the energy of a vaporizing mountain, and the question of how hard it is simply falls out of the arithmetic. It moves like anything else would move, like water or sand or air, because at those pressures, everything moves the same way. The crust around the impact didn't have to melt to do this for the most part. It flowed while still solid, the way a thick liquid flows, because at those pressures, the line between solid and liquid stops meaning very much. This was the second act of what the shock had begun. The shock wave, the front of compression that raced out through the rock in the first half second, delivered the energy, crushing and heating everything it passed through, and then, as such fronts do, it weakened with distance and ran on down into the deep earth to become an earthquake. But a shock passing through rock doesn't, by itself, dig a hole. It squeezes the rock and moves on, and the rock would mostly spring back. The hole is dug by what comes behind the shock, a slower, organized movement of rock, set going as all that compressed material is released toward the only opening available to it, which is up, toward the sky and the vanished sea. The shock was the blow, the flow was the splash, and the splash, being slower, took longer. It was still opening the ground at the count of 10 and would go on widening the hole for the better part of a minute after that. The cavity that opened was, for a few minutes, one of the most extreme features the surface of this planet has ever carried. At its widest, before gravity began hauling it back in, it was something like 100 kilometers across and close to 30 kilometers deep. Deep enough to hold the deepest ocean trench nearly 3 times over and still leave room at the top. Set it down on a map, you know, and its rim would run from one major city to the next, with a pit between them that fell past the bottom of the deepest sea, down toward where the cool crust gives way to the hot rock of the mantle below. That crust, the thin, solid shell the entire living world sits on, the only part of the planet anything has ever stood on or burrowed into or called home, is only about 30 kilometers thick here. For a few seconds, the hole reached very nearly all the way through it. It was, briefly and literally, a hole in the floor of the world. A pit that's steep and that deep cannot keep its shape. Its walls were already sagging back even as it widened, so the sharpest version of it lasted only a moment before the planet started in on the long work of closing it again. But that is a slower story. In the first 10 seconds, the ground was still tearing itself open. All the rock the splash threw upward had to go somewhere, and it went in 2 very different ways. Most of it rose as the crown, an expanding wall of shattered and half-melted rock lifting and spreading outward from the rim, the curtain of a splash 100 kilometers wide. That material was heavy and comparatively slow, and most of it would come back down not far from where it left, raining onto the ruined land around the hole. But above the crown, rising faster and reaching higher, was the plume, the vapor from the first half second, the boiled remains of the asteroid and the seabed, a column of glowing gas climbing off the wound and pushing up through the very hole the asteroid had already torn in the atmosphere. The crown was going up and coming back. The plume was going up and not coming back. Not here, anyway, and not for a long time. 3 things were leaving the scene at once, each at its own speed, and from a distance you would have met them in order. From a few 100 kilometers off, on that nearest land, among the last of the animals that had no idea any of this concerned them. The first to reach you would have been the light, the glare of the plume, arriving as fast as light arrives, which is to say at once. Then, some seconds later, the ground itself, as the earthquake the shock had become, rolled out through the crust and arrived under your feet, a shaking larger than any the planet has produced in all of recorded human history, throwing down everything that stood. And then, last and slowest, long after the light and the ground, the air, a wall of wind moving out from the impact faster than any storm, yet still only creeping compared with the light and the shaking, minutes away for anyone far enough off to be standing when it came. You would have seen it and felt the ground go, and only much later heard it, in that order, with long silences in between. It would be natural to think the whole was the disaster, that a wound 30 kilometers deep and 100 wide, an earthquake that knocked down a hemisphere, was the worst the day had in it. It wasn't, and the reason it wasn't has nothing to do with the whole. The whole was local. The earthquake, for all its size, was local too. It spent itself in the rock and faded. What turned a violent local event into a planetary one was not going down into the ground at all. It was going up. The plume climbing off the crater, the fastest of the thrown material racing up through the torn atmosphere. That was what carried the day to the rest of the world, and where it was going and how is the part that settled what kind of planet the morning would leave behind. Up to now, everything in this story has happened in one place. A single patch of sea over a single buried crater, a few 100 kilometers of ruined coast at the very most. That is how the mind wants to hold it, and it is how it is almost always drawn. A tremendous explosion in Mexico. But a single explosion, however enormous, is a local thing, and a local thing cannot end a world. To end a world, you have to reach all of it, every coast, every continent, the far side of the planet from the blast, and a hole in the Gulf of Mexico has no obvious way to touch the far side of the planet, except that it did. The reaching is the whole story, and the reaching had already begun in the plume going up. The plume kept climbing, a churning column of vaporized rock and metal, the boiled asteroid and the boiled seabed mixed together. And as it rose, the hole the asteroid had punched on the way down mattered a second time. Coming in, the asteroid had shouldered the atmosphere aside and left behind it for a few seconds a near-empty channel, a tunnel of thin air running from the ground all the way to the edge of space. The plume found that tunnel and poured up through it, meeting almost nothing in its way, venting out the top of the atmosphere into the near vacuum above before the air could close back over the wound. The same thinness of the sky that had failed to stop the asteroid coming in now failed to hold the consequences down. Once that material was above the air, the ordinary rules of falling stopped applying to it. Down here, anything you throw is fought the whole way by the atmosphere and pulled straight back to the ground by gravity, so it lands about where you'd expect. Up there, in the emptiness above the sky, there is nothing to slow a moving thing at all, only gravity quietly bending its path into a long curve. And the fastest of the thrown rock was moving at 5, 8, 10 kilometers a second, fast enough that the curve gravity bent it into didn't come back down anywhere nearby. It arced up and out over the round shoulder of the planet, the way a ball thrown hard enough would clear the horizon instead of dropping into the next field. Except this was thrown hard enough to clear whole oceans. Some of it travelled most of the way around the world before it came down. A little of it the very fastest, was flung clean off the Earth entirely, never to return, scattered out into the spaces between the planets, where some of it may be drifting still. As that vapor climbed and spread and reached the cold top of its arc, it did what any vapor does when it cools. It condensed, not into raindrops, into rock. Countless tiny beads of molten glass, most of them smaller than a grain of rice, froze out of the plume all across the upper sky. A fine glassy rain hung above the whole planet and beginning very slowly to fall. The crater had been turned inside out and thrown over the world as a haze of small glass spheres. Enough of them came down in the end to leave a layer you can find today on every continent and under every ocean. A thin, dark seam in the rock, a few millimeters thick in most places, that marks this single afternoon across the entire face of the Earth at once. Geologists can stand on almost any old enough piece of ground anywhere in the world and lay a finger on the line. It is the same line everywhere. There is no other day in the whole history of the planet written down so completely, in so many places, in so little space. Some of those beads will fall in the hours after the impact on places that have no names yet and won't for tens of millions of years, including somewhere the ground you happen to be lying on tonight. The continents weren't where they are now. The country you live in may have been open sea floor then, or sitting somewhere else on the map entirely. But wherever the land that would one day be yours was resting that afternoon, a share of this glass was already on its way down toward it. There's a fair chance that if you dug far enough, straight down from where you are, you would come to it. The same thin line, the same little spheres, the afternoon still lying there in the dark, beneath everything that has happened since. By the count of 10, the throwing was done. The asteroid was gone, the crater was dug, the plume was away, and the planet had flung a piece of itself clear across its own sky. For the first time since the morning began, nothing new was being added. The energy had all been spent, the material had all been launched. The planet simply waited. Above it, all the way around it, the glass it had thrown hung at the tops of its arcs, slowing, turning over, starting to come back. It would take a few hours, and when it came down, all of it, everywhere, more or less at once, the second way this day killed would begin, and that one would not need the crater at all. On any clear night, the sky performs a small and harmless version of what came next. A speck of rock or dust drifts in from space, meets the top of the atmosphere, and the friction of its own speed turns it into a streak of light, a shooting star, gone in a second. That streak is the speck's motion becoming heat as the air refuses to let it through. The rock arrives fast. The air won't part for it at that speed, and the difference is paid out as light and warmth, high up, where almost nobody feels it. Now run that same trick with everything the impact had flung above the sky. Not one speck, but a good fraction of a mountain, broken into countless beads of glass, all of it falling back into the atmosphere across the whole planet within the same few hours, a few hours after the morning had ended. Billions upon billions of those beads came down together, and every one of them did what the shooting star does. It braked high in the air and gave up its motion as heat. One alone would do nothing you'd notice. All of them at once turned the upper atmosphere, the whole shell of it, wrapped around the entire planet, into a layer of glowing, red-hot sky. Not a single point of light crossing the dark, but the dark itself lighting up everywhere, from horizon to horizon and on around the curve of the world. The heat was worst near the crater, as you'd expect, but it was also strangely concentrated on the exact opposite side of the planet, the point directly across from the impact, where the arcs of thrown glass, having gone up and over in every direction, came down and met again. There was nowhere on Earth the returning sky entirely passed over. A sky that glows like that does not keep the heat to itself. It radiates downward onto everything beneath it, and there was a vast amount of it. The entire dome of the sky pouring heat onto the surface from every direction at once. Down on the ground, the strength of that downward heat reached something like 7 times the force of the midday sun, and it held there not for the moment a sunbeam takes to cross a gap in the clouds, but for 1 to several hours. The nearest thing in ordinary life is the top element of an oven, the broiler, glowing and aimed down at whatever sits beneath it. For a few hours, the whole sky was that element, and the surface of the planet was what lay underneath. The air near the ground did not, for all that, become an oven in the sense of hot air. It barely warmed, a few degrees at most, because air is mostly transparent to this kind of radiant heat and lets it pass straight through, the way the air in front of a fire stays breathable even while the fire burns your face. So an animal in the open could go on breathing ordinary air right to the end. What it could not do was stand under an entire sky that was glowing like a grill. Anything turned toward that open sky, leaves, skin, the dry surface of the ground, took the full weight of the heat and began climbing toward the temperature of cooking. The danger that hour, then, was not the hot wind or the smothering air you might picture a great fire bringing. It was light, the infrared glow of a planet's worth of returning glass, falling on everything that had nothing above it. So whether you lived through that hour came down to a single question, and it was not the one you'd expect. It was not how large you were, or how fast, or how high you sat in the food chain. A tyrant dinosaur and a creature the size of a sparrow stood in exactly the same danger if they stood in the open. The only thing that mattered was whether there was something between you and the sky. Underwater, even shallow water, you were safe. Water drinks that radiant heat in its first few centimeters and never passes it down. Under rock or inside a fallen log, you were safe. And underground, in a burrow, a den, a tunnel, you were safest of all, because soil is very nearly a perfect shield. The heat soaks into the top millimeter of dirt and goes no deeper, so that an animal a hand's depth down would have felt the ground above it grow warm, and then, hours later, cool again, and never known how close the thing overhead had come. A few centimeters of ordinary soil was the whole difference between living and dying that afternoon across the entire surface of the world. That much the physics makes reasonably clear. What came of it is where the honest version of this story has to slow down and admit how much it doesn't know. A heat like that, poured onto a world full of dry wood and dead leaves, ought to have started fires, and for a long while the picture was of a single global firestorm, the whole land surface of the planet catching at once, with a layer of soot in the rock that seemed to confirm it. But when researchers went looking in the boundary layer for the charcoal a worldwide forest fire should have left behind, in a great many places they found very little, and found instead plenty of plant matter that hadn't burned at all. Others pointed out that the first beads to fall would have hazed the upper sky and shaded the ground from the beads still coming, so that the heat actually reaching the surface may have been far less and far patchier than the simplest sum suggests, a fizzle in places rather than a firestorm. And some of that soot, it turned out, may not be burned forest at all, but the carbon of the unlucky seabed itself, the buried oil and rock vaporized in the impact and scattered with everything else. The likeliest truth is some uneven mixture, fierce fires in some regions, little or none in others, a world scorched in patches rather than evenly broiled. Exactly how much burned and where is one of the genuinely open questions about that day, and anyone who tells you they know for certain has run out ahead of the evidence. A whole planet is hard to hold in the mind at once, a glowing sky, a scorched and uneven world, countless animals living or dying by whether they happen to be under cover. so it helps here to narrow all the way down from the burning planet to a single place, a quiet river valley a long way north of the crater, on the shore of a shallow inland sea where the water had just begun to do something strange, and where this 1 hour, not the day, the hour, was about to be written into the rock with a completeness almost nothing else in the planet's history can match. The record turned out to be a fish. Many fish, in the end, but it's easiest to begin with one of them, and with one small part of it, the gills. 66 million years after that afternoon, a paleontologist working the Badlands of North Dakota split the rock around a fossil sturgeon and found, caught in the fine comb of its gills, dozens of tiny spheres of glass. Not washed in long afterward, lodged in the gills where they could only have come to rest one way. The fish had been breathing, pulling water across those gills to take the oxygen out of it, while the glass was in the water. It had inhaled the spheres, alive, and then died before it could clear them. And we know exactly what those spheres are, because we have already watched them form. They are the cooled droplets of the plume the crater turned to glass and flung across the sky, fallen back to Earth. The fish had breathed in the impact. You can read the hour of its death straight off its own body. The place is called Tanis, a fossil site in the dry hills near the western edge of North Dakota, and at the time it was the mouth of a river on a low plain, joined to a large body of inland water, a remaining arm of the shallow sea that had not long before split the continent down its middle. It sat about 3,000 kilometers from the crater. That was far enough that the blast never reached it. Far enough that the giant wave the ocean would eventually raise was still many hours out. Far enough that on any ordinary day, nothing happening down in the Gulf of Mexico would have meant a thing this far north. But this was not an ordinary day, and 3,000 kilometers, it turns out, is no distance at all to an earthquake. In the first minutes after the impact, nothing here has changed. The light of it has already come and gone, aglow over the southern horizon. The sound is still hours away, crawling north through the air. And then, around 6 minutes in, the ground arrives, the earthquake rolling up through the crust from the crater, reaching this riverbank first as a tremor, and then, within a few more minutes, as a hard and building shudder. You are standing on the bank as it comes. The water in front of you, the river and the broad, shallow sea it runs into, feels the same shudder, and a body of water that size does not take a shaking quietly. It begins to slosh, the whole sheet of it tilting and rebounding, the way bath water heaves if you shove the tub, except that this tub is an arm of an ocean. The water climbs the bank toward you, falls back, climbs again, higher each time. And then, while the water is surging, the sky begins to deliver its glass. Somewhere between 13 and 25 minutes after the impact, that is how long the spheres take to finish their arcs and fall this far north. The first of them come down, hissing into the river, into the heaving sea, onto the backs of fish driven into the shallows by the rising water. The fish are still alive. They are breathing hard, the way anything breathes hard in churning water, and with every breath they draw the falling glass across their gills. The surge piles them together, sturgeon and paddlefish tangled with snapped branches and torn up plants and the bodies of other animals. And then it buries them, fast, under a load of sediment. The same sloshing water has thrown up deep enough and quick enough that the spheres in their gills never wash out. That is why, 66 million years on, the glass is still there to find. And it is not the freak of a single fish. More than half of the sturgeon and paddlefish taken from that layer carry the same glass in the same place. They were buried at the very moment the sky was raining the crater back down, and they carried the proof of it into the rock. It's worth being precise about what the water was, because the easy guess is wrong. This was not the Great Ocean Tsunami, the wave the crater raised in the Gulf, which was real and was coming, but was still the better part of a day from reaching anywhere this far inland. The water that drowned the fish at Tanis was local and immediate. The inland sea itself, sloshing in its own basin from the force of the quake, throwing up surge after surge in the first hour while the tsunami was still out crossing the world. The two waters arrived at this one spot something like a day apart, and it was the early one, the earthquake's water, that did the burying. The timing is the whole point. The spheres were falling in those first minutes, the surge was burying in those first minutes. The two clocks agree. Whatever else is uncertain about Tanis, the rock says these animals died inside the first hour of the new world, while the old one was still coming down out of the sky. The rock says something finer still than the hour. Fish grow in layers, a little like trees, laying down more bone in the seasons of plenty, and pausing in the lean cold, so that a slice through a fin spine or a jaw holds a record of the years and the seasons the animal lived through, right up to its last one. When researchers read those final layers in the Tanis fish, the growth had stopped partway into the season of plenty. The animals had died in spring, the northern hemisphere's spring, the year's growth begun but not yet finished. Two different teams, working from different bones by different methods, arrived at the same season. So we can say of a single afternoon, 66 million years, gone not only the hour of it, but the time of year. It was spring in the north when the sky came down. All of this has to come with a caution, spoken plainly, because Tanis is at once the most vivid window we have onto that hour and the most argued over. The man who found it, a paleontologist named Robert De Palma, told much of the story to a magazine writer before the scientific paper appeared, and some of the most spectacular claims attached to the place, a preserved feather, a dinosaur said to have died that very day, have shown up in documentaries and interviews more than in the reviewed literature, which is the wrong order, and which made a good many careful scientists wary. There was also a sharp public fight over the data behind the spring season finding, serious enough that a journal flagged the reliability of the figures and an inquiry concluded the data had been handled badly, though nothing had been invented. None of that erased the core of the site. The spheres in the gills are real. The drowned, buried fish are real. And the spring timing was confirmed separately by another team whose work has held up. The honest position is to hold both things at once, that Tanis may be the closest we will ever stand to the hour of the impact, and that some of what has been said about it has run out ahead of what has been shown. The fish are not in doubt. A few of the louder claims around them are. Within that first hour, the earthquake's water finished what it was doing and began to fall back. The fish sealed into their sediment, the record made. It was, for all its violence, a small and local thing, an inland sea shaken in its basin, settling now toward calm. The ocean's own answer to the crater was neither small nor local, and it was not settling. It was still out there in the dark of the open water, far to the south, far larger than anything that shallow seaway could ever raise, and it had 2 more days to run. An hour after the impact, the wave was already out in the open gulf, and from anything floating on the surface, it would have been almost impossible to see. Out in deep water, a wave like this doesn't rear up into a wall. It runs low and stretched out and very fast. A long, humped swell tens of kilometers from front to back, racing at the speed of an airliner, lifting a ship 100 meters and setting it down again so gradually that no one aboard would feel much more than a slow, vast heave. All of the violence was in how much water was moving and how fast and how far it still had to go. To see how one hole in one shallow sea could put that much ocean in motion, you have to go back to the hole. When the asteroid struck, it had shoved the shallow sea aside and dug the seabed into a deep, dry pit, a hole in the ocean, kilometers down, with no water in it. An ocean will not leave a hole like that alone. From every side, the surrounding sea rushed in to fill the gap, converging walls of water that met at the center with nowhere left to go but up, rebounding skyward in one enormous splash, taller than the pit had been deep. That rebound falling back, the crater's drowned rim sliding inward, the rain of thrown rocks striking the sea for hundreds of kilometers around, all of it set the surface heaving outward in a spreading ring, and the first crest of that ring, close in, stood something like 4 kilometers high. That was the wall of water you might picture. By the time it reached the open gulf, it had already come down out of the sky and stretched into the long, fast swell. But it had begun as a mountain of seawater taller than the hole that raised it, and it did not stop at the gulf, because in those days the gulf did not close itself off the way it does now. The wave poured north and east into the young Atlantic inside the first hour. Southward, where today an unbroken bridge of land joins North and South America, there was then an open seaway between the two continents, and the wave ran straight through it into the Pacific within a few hours. And the Pacific is the largest single thing on the face of the Earth, and it crossed that too. By the end of the first day, the disturbance was running through most of the Atlantic and most of the Pacific at once. By the end of the second, in some worn-down form, it had reached very nearly every coastline on the planet. One hole in one shallow sea had set every ocean in the world moving. The deadliest tsunami in living memory crossed the Indian Ocean at the end of 2004 and killed something close to 250,000 people. It is the largest such wave human beings have ever measured. The wave from the crater carried, by the best modelling we have, on the order of 30,000 times its energy. Not 30 times, 30,000. The far-travelled, worn-out version that came ashore 10,000 kilometres away, at the very end of its journey, still arrived taller than the 2004 wave managed at its worst. Set against that one day, the most destructive tsunami in all of human history would have been a rounding error. Distance made it slower and lower, but never gentle. Even 10,000 kilometres out, the surging of that water along the bottom was strong enough to scour the deep sea floor, to sweep away the fine sediment that normally settles there a grain at a time across the ages, and leave behind, in the rock, a clean gap where a stretch of time has simply gone missing. Those gaps, and the churned and scattered deposits that come with them, turn up along the paths the model draws for the wave, whole oceans away from Mexico, disturbed seafloor off what is now New Zealand, more than 12,000 kilometres from the crater, lying just where the water should have run hardest. And nearer in, beneath the flat farm country of southern Louisiana, buried and silent, lies a field of giant ripples pressed into what was then the sea floor. Ripples over a dozen meters high and some 600 meters from one crest to the next, the print of a single wave passing through. That country will be dry and ordinary one day, a road laid across it and a crop standing on it, and the ripples will still be down there in the dark under the soil, so that you could drive that road or stand in that field and never once suspect that the deep ocean had reared up and run through it for 2 days, 66 million years before there was a field or a road or a you to wonder about any of it. We don't really have a word that fits this. Tsunami brings up one wave on one coast, a terrible afternoon in a single place. A giant wave is worse, because it makes you see one wall of water, one strike, one withdrawal, over. What happened was neither. It was the entire ocean, every ocean, set moving at once. A train of waves crossing and recrossing the deep for 2 full days, scraping the seafloor on the exact far side of the planet from where the rock came down. It had no single coast and no single wave. It was only the whole sea in motion, long after the fire overhead had faded and the great earthquake had wrung itself out, long after the crater that started it had gone quiet. Though quiet is not quite right either. While the wave was still 2 oceans from finishing, the hole itself back in the Gulf, had stopped throwing water and rock into the sky and begun to do the reverse. To fill, the sea sliding back into the wound and the thrown rock settling out of the air on top of it, layer over layer, about as fast as rock has ever been stacked anywhere on Earth. The clearest record of that first day, written down in order and sealed where almost nothing could disturb it, was not out on the open ocean at all. It was at the bottom of the hole. What lies at the bottom of that hole is, today, buried rock beneath the floor of the Gulf, and a long time after the impact, people went and got it. They drilled down into the old crater from a small platform jacked up in the shallow water off the Yucatan coast, brought the rock up in sections the width of a dinner plate, and laid the day out on tables in the order it had fallen. You can stand and look at it, a run of dull, broken stone, grey and brown, melt and rubble and grit, 130 metres of it from bottom to top, and the whole of that 130 metres is a single day. Most layers of rock that thick stand for a long, slow stretch of time, an age, a span too vast to feel. This one stands for a day. The day the asteroid came down, written out at a thickness no ordinary day on this planet has ever been given. The drilling was done in 2016 by an international team working over the buried centre of the crater. They had gone after the deep structure of the impact, the ring of rock the collapse had heaved up from kilometres down, and they got that. But the drill had to pass through the first day to reach it, and the first day turned out to be the real prize. Sean Gullick, one of the scientists leading the work, called the corid stretch the first day of the Cenozoic. The Cenozoic being the long age of the world that begins at this boundary and runs, unbroken, all the way to now. The name is exact. The bottom of that core is the last hours of the old world. Everything above it is the first hours of ours, and the two sit a few meters apart in a single piece of stone you could carry. Read from the base up, the day arrives in order. At the bottom is the melt, rock that ran liquid in the first instant and then froze, the floor of the crater itself, the moment of impact turned to stone. Above it, the rock changes, and the change marks the clock striking somewhere in the first hour. This is where the sea came back. The water the impact had blown away rushed back into the empty hole, perhaps 30 minutes to an hour after the strike, and it came back filthy, loaded with shattered rock and melted glass and grit torn off the sea floor, and it dumped all of it into the crater in one vast sorting flood. On top of that lie the marks of the hours that followed, the same water trapped in the basin, sloshing back and forth as the great waves and the local surges ran through it, each pass laying down a graded sheet of debris, the coarse settling first and the fine settling last, over and over, something like 25 sheets stacked one on the next, 25 slow breaths of a drowning crater, and carried in among the debris there is charcoal, burnt wood washed off the land nearby, so that even the fires of that afternoon left their line in the rock at the bottom of the sea. Then there is something missing from the rock, and the absence matters more than almost anything present. The seabed the asteroid struck was rich in sulfur, those thick beds of gypsum, the sulfur locked in stone. By rights, the rock that records the impact should be full of it. It is nearly empty. The sulfur is not in the crater because the sulfur did not stay on the ground. It was vaporized in the first instant and flung up with everything else, and unlike the heavy rock that fell back and filled the hole, it stayed up, a great load of it, climbing into the high air as gas, where it would become a fine pale haze and do the slow, patient work that the fire and the wave and the earthquake, for all their violence, never could. The crater kept the rubble, the sky kept the sulfur. You can measure how much of it left by how little of it stayed. At the very top of the day, capping the 130 meters, lies a thin layer of a different kind, fine and rich in a metal called iridium, which is rare in the Earth's crust and common in asteroids, and which is almost certainly the dust of the visitor itself, ground up, scattered, and at last coming to rest. But this layer did not settle in an hour or in a day. The rubble below it was dumped fast in the flood and the sloshing. This last fine skin drifted down slowly out of water and air that stayed clouded with the impact's finest dust for a very long time. It took months. It may have taken years. So the rock does a strange thing at the boundary. The 130 meters beneath the cap record a single day, and the few centimeters of the cap record the years that followed, and the years are written thinner than the day. The day was thick because it was loud. The years were thin because they were quiet, and the quiet, it would turn out, was the most dangerous part of all. It is a strange thing to be able to hold. Most of the days in the planet's history left nothing behind at all. No layer, no mark, not a line you could put a finger on. The overwhelming majority of all the days that have ever happened on Earth are simply gone, summed away into the slow blur of the rock. This one was kept in full, in order, 130 meters of it, because for a few hours the planet was moving fast enough and breaking enough rock to write at a speed the rock could hold. There is no other day quite like it down there, and then at the top of the day the rock goes quiet. The last fast layer is laid down, the sloshing stops, the flood drains away. What is left to settle is only that fine, slow dust, drifting down through water and air for months and years, and the reason it took years is the whole of what came next. The dust came down so slowly because the sky stayed full so long, and while the sky stayed full, very little light reached the ground. The day was over. The dark was not. The thing the sulfur had gone up to do and the thing the dust was doing as it fell were the same thing, and it lasted not for hours, but for years. The long winter the planet had been thrown into, the part of the whole event that did the most of the killing, and by far the slowest. Almost all of the warmth on this planet is borrowed. The Earth makes a little heat of its own, deep down, but at the surface it counts for almost nothing. The warmth you live in, the liquid seas, the mild air, the simple fact that water runs instead of standing as ice, is very nearly all of it sunlight, arriving fresh each day and leaking back out into space each night in a balance so steady it feels like a property of the planet rather than a thing being delivered. It is not a property of the planet, but a delivery, and a delivery can be interrupted. By a few weeks after the impact, the delivery had been interrupted across the entire world at once. The sky had closed. Not with cloud, you can see through cloud and rain falls out of it within days, but with something finer and far more stubborn, a haze of tiny particles lifted into the high air by the impact and spread around the whole planet, thin enough to be nearly invisible and dense enough together to turn day into a deep and lasting dusk. Beneath it, the sunlight reaching the ground fell to a fraction of what green things need to live. And it stayed that way, not for an afternoon, not for a season, but for something close to 2 years. What the haze was made of is a question worth coming back to, because it is genuinely unsettled, but how it worked is not much in doubt. To dim a whole planet, you don't need a wall. You need a veil, and you need it high and fine. Particles small enough, specks 1,000th of a millimeter across, or smaller, are very good at getting in the way of light, far out of proportion to their weight, scattering and soaking up sunbeams that would otherwise have reached the ground. And lifted high enough above the weather, there is almost nothing to bring them down. No rain up there to wash them out, only the slow drift of settling, which for the finest particles takes years. So a relatively modest amount of the right material, ground fine and thrown high, can hang over the entire Earth like a held breath and simply stay there, turning the sun to a dim coin, and then, in the worst of it, taking even the coin away. And here is the turn the whole story has been building toward. Everything loud about that day. The fireball, the thrown sky, the wave that crossed the oceans, the earthquake that knocked down a hemisphere, was, in the end, local and brief. Terrible where it happened, and over within hours or days. The thing that reached every living place on Earth and stayed for years was none of those loud things. It was the quietest of them. Fine particles, high in the air, doing nothing more violent than standing between the ground and the sun. Of everything the impact did, the deadliest turned out to be the simplest. It put out the light. With the light went the warmth, and the cooling followed close behind. Within weeks, the surface of the land had begun to drop, and it kept dropping, and where the models disagree on the details, they agree on the shape. A fall of something like 25 or 30 degrees across much of the land into a cold the Cretaceous world had no defense against and no memory of. This had been a hothouse planet. No ice at the poles, warm seas lapping over shallow continents, ferns and forests growing where there is tundra and ice today. A world like that does not know what to do with frost. And across the middle of the continents, summer temperatures crossed below freezing. Even tropical coasts that had never in their existence known a cold night were pushed toward it. The planet had been thrown into a winter, a real one, not a turn of phrase, a global and sunless winter, and it would not lift for years. This is the long winter, the cold that comes after the very largest things the Earth can do to itself. And of all the long winters in the planet's history, this was among the longest and the deepest. The dark you're sitting in right now, wherever you are, is the thin and friendly version of this. It comes every night and it lifts every morning. You can feel, somewhere beneath thought, that the light is coming back, the way it always has. Take that nightly dark and stretch it, not into a long night, not into a polar winter that you know will end, but into 2 years in which the sun never quite returns, in which every noon is dimmer than a heavy dusk, every plant is starving, and the cold deepens month over month with no turn of the season to promise relief. That is nearer to what the survivors lived inside. Not a dark that fell and lifted, but one that fell and stayed. What that haze was actually made of is one of the liveliest arguments in the field, and it's only honest to say it isn't settled. There were 3 candidates, and all 3 were up there. There was sulfur from the vaporized seabed, the load the crater failed to keep, turned to a fine reflective haze that lingers for years. There was soot, the black carbon of burned forests and burned oil, darker and better at swallowing light outright. And there was rock dust, the impact's own pulverized stone, ground in the worst case to grains so fine they can drift for more than a decade. For a long time, the sulfur was thought to be the main culprit. More recent work has argued that the fine rock dust may have done more of the dimming than anyone expected, with the soot close behind and the sulfur a smaller player than the old numbers held. And the old numbers for how much sulfur there even was have themselves been cut lately by a large factor. The arguments are technical and ongoing, and they matter for the exact depth and length of the dark. What none of them touches is the result. By every account, the sky closed, the light failed, and the cold came and stayed for years. The disagreement is over which hand turned the lamp down, not over whether the room went dark. And in a world that runs entirely on sunlight, the first thing a failed sky reaches is not the warm-blooded, or the large, or the fierce. It is the green. Every leaf on every plant, every cell of green scum and drifting plankton in the sea lives by catching light and building food out of nothing more than air and water, and there was no longer enough light to build with. In the bright surface waters of the oceans and across the darkened land, the green things began, very quietly, to stop. A few months in, the forests had gone strange in a way that was quiet rather than violent. The trees still stood, most of them. Nothing had knocked them down. But they were bare, stripped of their leaves, not by a storm, not by a passing season, but by the slow failure of the light that leaves exist to catch. A leaf is a small machine for turning sunlight into food, and a machine with no power running to it is only a cost, so the trees had let their leaves fall, the way a plant does in a drought or a hard winter, and stood waiting in the cold and the dimness for a spring that did not come. On the forest floor, the ferns and the low green things, which could not afford to wait, were already dead or dying. The forest was not burning. It was not flooded. It was simply going out from the ground up like a fire running backward, and what fed on the green went out behind it, in order. The machinery of a mass extinction, seen plainly, is almost absurdly simple. Every animal that has ever lived is, in the end, eating sunlight. The plants catch the light and turn it into themselves. The plant eaters eat the plants. The meat eaters eat the plant eaters, and a few things eat the meat eaters. It is a tower built entirely on its bottom layer, on the green, on the light. Take the light away, and the tower does not fall all at once. It comes down from the bottom up, floor by floor, in sequence. The plants go first. Then the animals that lived directly on plants begin to starve. Not in a day, but over the weeks and months as the last stored food runs out. Then the hunters that lived on those animals follow them down a little later for the same reason. The large and the fierce did not die first because they were strong enough to outlast the rest. They died last because they stood furthest from the light, at the top of a tower whose ground floor had already given way. If you had been alive inside it, any animal, anywhere, you would not have experienced an impact. The impact was a single afternoon on the far side of the world, and you almost certainly missed it. What you would have lived through was a winter that refused to end. The days came dim and grew dimmer. The cold came and deepened. The food thinned and then was gone. There was no event to it after the first day. No enemy, no fire, nothing to run from. Only a world getting quieter and colder and emptier around you, month after month, while you grew weaker, until one of the cold, dim mornings was simply your last. For almost everything that died, the end was not a catastrophe witnessed, but a slow subtraction endured. The same thing was happening in the sea, on the same logic and in the same order. The surface of the open ocean is a kind of invisible meadow, not of plants you could see, but of countless drifting single-celled things that live by catching light, the green base of nearly every food chain in the water. When the light failed, that meadow failed with it, the top few meters of the entire world ocean at once, and everything that grazed on the meadow and everything that hunted the grazers, the small swimming things, the fish, the coiled ammonites, the great reptiles at the top, came down floor by floor in the same slow order in a sea that had lost its grass. But the sea held a second death the land did not, and it fell hardest on the very creatures that should have been best protected. A great many ocean animals, from the smallest plankton to the ammonites, build their bodies out of shell, armor and skeleton made of the same stuff as chalk and limestone, drawn straight from the seawater around them. That trick only works while the seawater stays on the right side of a chemical line and the impact had shoved it across. The sulfur and the carbon flung up from the shattered seabed came back down, in part, as acid, sulfuric and carbonic, raining into the sea and soaking into its surface. And acid dissolves shell. Within 1,000 years, fast by any ocean's reckoning, the surface waters turned measurably sour. Sour enough that building a shell grew harder, and holding on to one became a slow defeat. So the armoured multitudes of the sea were caught twice over, starving in the dark and dissolving in the water that was meant to hold them up. The creatures that had spent an age armoring themselves against the ordinary dangers of the sea found, in the worst of it, that their armor had turned against them. It's worth saying plainly where the dying actually got done, because the shape of the story tempts you to get it wrong. The fireball and the wave and the earthquake are what a film would show you, the loud hour, the spectacle, and they did kill fiercely near where they happened. But add them all together across the whole planet, and they account for a small share of the dead. The overwhelming majority of everything that died, on land and in the sea, died later and quietly. Of the dark, the cold, and the sour water, starved, frozen, or dissolved over months and years in a world that had simply stopped working. The asteroid killed, in the end, not by striking the Earth, but by changing its sky, and then letting the changed sky do the rest. The loud part was the smaller part. The grief of it is in how slow and how quiet the larger part was. All of that dying, every starved plant-eater and every dissolving shell, every lineage thinning away across every continent and every ocean through those years, does in the end add up to something you can put a number on. People have counted it as nearly as such a thing can be counted, and the figure they reach is among the harshest in the whole history of life. A single number that stands for the emptying of the world. The popular picture of all this is a single image, great dinosaurs alive and thriving one afternoon, gone by the next, and it is one of the most familiar pictures in all of science. It is also wrong in two separate ways at once. It is wrong about the speed, because almost nothing died that afternoon. The dying took months and years, the slow subtraction we have just watched. And it is wrong, or at least far too sure of itself, about the word thriving, because whether the dinosaurs were flourishing right up to the end or already fading is a question the evidence has not settled and may not be able to. The image gets the drama right and the facts mostly wrong, which is the usual trouble with images. What is not in doubt is the size of it. When paleontologists tally the species that vanish at this boundary, counting, as nearly as the fossil record allows, what lies below the line and is gone above it, they arrive at a figure of roughly 3 in every 4. About 75% of the species alive on Earth, in the fullest count we have, did not cross from the world beneath that thin, dark layer to the world above it. 3 of every 4 kinds of living thing erased inside the span of a few years. It is worth slowing down on that number because the mind slides off it. Not 3 in 4 individuals. Individuals die all the time in every year there has ever been. 3 in 4 species. 3 of every 4 distinct ways of being alive. Whole kinds of creature gone with no survivors, no remnant, no return. The roll of the dead is long, and the dinosaurs are only its most famous line. Every dinosaur that was not a bird, every last one, the whole long dynasty, gone. The flying reptiles, the pterosaurs that had owned the air for as long as the dinosaurs had owned the ground, gone with them. In the sea, the great marine reptiles, the mosasaurs, and the long-necked plesiosaurs, the top hunters of every ocean, gone. The ammonites, the coiled, shelled creatures that had filled the seas for more than 300 million years through extinction after extinction, this time vanished altogether, every species of them. The reef-building clams went, whole families of plankton went, but the famous picture leaves out the largest part of the toll. Most of what died was not big and was not on land, and would never have made it into anyone's painting. The overwhelming majority of the dead were tiny, drifting plankton, small shelled things in the sunlit top of the sea, the green base of the ocean, and the countless creatures that grazed on it. The dinosaurs are the face of this extinction. They were never the bulk of it. To set a number like 3 in 4 against anything, you have to reach for the few other times the planet has done something comparable. And there are only 5 in the whole history of complex life. 5 mass extinctions, severe enough to stand out from the steady background of ordinary loss. This was the most recent of those 5, the end of the Cretaceous, the one that took the dinosaurs. And it tends to unsettle people to learn that it was not the worst of them. The largest, by a wide margin, had come 200 million years earlier at the end of the Permian, when something close to 9 in 10 marine species died and life on Earth came nearer to ending outright than at any other moment we know of. The extinction that ended the dinosaurs, the most famous catastrophe in the planet's whole story, the one with its own image, ranks among the great die-offs somewhere in the middle. The Earth has emptied itself this thoroughly 5 times over. This was one of the smaller 5. That leaves the harder question, the one the famous image gets wrong by being too certain. Were the dinosaurs thriving when it came, or already on their way down? You can find serious, careful scientists on both sides, and the disagreement is genuine. One camp, reading the fossils of the last stretch of the Cretaceous, sees the variety of dinosaur kinds already shrinking for millions of years before the impact, fewer new forms appearing, old ones dying out unreplaced as the climate slowly cooled. By that reading, the asteroid fell on a dynasty already thinning and finished something that had started without it. The other camp answers that the thinning is a trick of the evidence. The rocks of those final million years are simply rarer and harder to read, and a gap in the record looks to anyone counting exactly like a decline. Correct for that bias, they argue, and the dinosaurs were as varied and as widespread at the end as they had been for ages, struck down in full health, not caught already falling. The most recent work leans toward caution, holding that the data we have cannot yet tell a true decline from a hole in the rock. So the honest answer is that we don't know. What both sides agree on is the only thing that mattered on the day. Declining or thriving, the dinosaurs were still here, still spread across the whole planet when the sky went out, and after it, they were not. It's the lineages that give the number its real weight. A species is one thing. A lineage is a way of being alive that has worked, sometimes for an enormous span of time. The ammonites had been coiling their shells and hunting the seas for over 300 million years, longer by far than there had been dinosaurs, longer than there had been flowers or birds or blades of grass. They had come through every earlier extinction, thousands of species of them across that immense run, and then, at this one boundary, the whole lineage closed, with no descendants at all. The dinosaurs, 150 million years of them, the largest animals ever to walk on land, closed too, but for the single feathered branch that became the birds. 3 in 4 is not, in the end, a number about death, which is ordinary and constant. It is a number about ending, about how many separate, ancient, successful experiments in being alive were shut permanently in the few years it took the dark to finish its work. And the strangest thing about all of it, the number, the role of the dead, the closed lineages, the dim afternoon and the darker years, is that for almost the whole of human history, nobody knew any of it had happened. The thin, dark layer had been there in the rock the entire time, on every continent, holding the whole story, and people walked over it and quarried through it and built their houses on it without the faintest idea what it was. How we finally came to read it, how a line in the ground became a falling mountain and a shut sky and 3/4 of all life, is a story of its own, and a surprisingly recent one. It begins the way a surprising amount of science begins, with one person turning over a piece of rock he couldn't explain. In the early 1970s, in a limestone gorge near the town of Gubbio in central Italy, a young geologist named Walter Alvarez kept coming back to a single thin seam of clay. The rock around it was orderly and beautiful, pale pink limestone laid down grain by grain on an ancient sea floor over millions of years, and packed, when you looked closely, with the tiny shells of plankton, But at one level, the shells below the clay were rich and varied, and the shells above it were sparse and small and strange, as though the sea had been emptied and then slowly, poorly, refilled. Between the two worlds lay the clay, a finger's width of it, dull and quiet, with almost nothing living in it at all. Alvarez wanted to know one simple thing about that clay: how long it had taken to settle. The answer would rearrange the planet's history. The way he chose to measure it was clever, and it came from his father, Luis Alvarez, a physicist, the kind of man who reached for a physics trick when a geology question got stuck. Their trick was a metal called iridium. Iridium is almost absent from the Earth's surface. When the planet was young and molten, nearly all of it sank with the iron into the core, and what little reaches the surface now drifts down slowly and steadily out of space, in the faint dust of burned-up meteors, at a rate that barely changes from one age to the next. So iridium is a kind of clock. A clay layer that took a long time to settle should have caught a lot of that slow space dust. A layer that settled quickly should have caught only a little. Measure the iridium, and you measure the time. The measuring was done by two chemists at a national laboratory in California, Frank Asaro and Helen Michel, and when the number came back, it made no sense as a clock at all. There was far too much iridium, 30 times the ordinary background at the Italian site, and when they checked boundary clays in Denmark and New Zealand, more still, the same impossible excess turning up on the far sides of the world. Too much iridium in too many places meant the metal hadn't drifted down slowly over ages. It had arrived all at once in quantity, and the only thing that delivers iridium in quantity is a piece of the early solar system striking the Earth. In 1980, the Alvarez team published the idea that a body perhaps 10 kilometers across had hit the planet at the end of the Cretaceous and thrown up a dust cloud that shut out the sun. It's worth being exact about what that paper did and did not do, because the popular memory gets it wrong. It did not name a crater. It did not show where the thing had landed. It did not, in any final sense, prove that an impact had killed anything. It offered a hypothesis, a chemical anomaly and an argument, and it left a very large hole in the middle of itself, shaped exactly like a missing crater. For 10 years, that hole was where the fight happened. A boundary layer full of strange metal was one thing. A 10-kilometer wound in the Earth that no one could find was another, and without it, the whole idea hung in the air. The crater, as it happened, had already been found by someone who wasn't looking for it and didn't know what he had. A few years before the Alvarez paper, a geophysicist named Glenn Penfield had been flying surveys over the Gulf of Mexico for a Mexican oil company, mapping the magnetism and the gravity of the buried rock for places worth drilling. Off the coast of the Yucatan, his instruments traced an enormous, startlingly round structure beneath the sea floor and the land. A ring nearly 200 kilometers across, far too big and too symmetric to be anything ordinary. Penfield suspected he was looking at the scar of a giant impact. In 1981, he and a colleague presented it at a conference to a room that was nearly empty. The people who might have cared were elsewhere, and the company's data was mostly locked away as proprietary. And so the crater sat there, found and unrecognized, a buried ring on a few forgotten maps for the better part of a decade, while a continent away the impact idea went looking everywhere for exactly it. What finally brought the two halves together was a graduate student and a piece of luck. Alan Hildebrand, hunting the impact site by tracing its debris through the Caribbean, heard, through a journalist who had been at that nearly empty conference, about Penfield's buried ring. He got in touch with Penfield. Together they tracked down old drill cores the oil company had pulled from the structure years before and left half forgotten in storage. In the rock was shocked quartz, grains deformed in a way only the pressure of an impact can produce, and that settled it. In 1991, more than a decade after the iridium and decades after that rock first came up the drill pipe, the crater was named after a small town on the coast above it, Chicxulub. The hole the 1980 paper had needed and lacked was real. It was the right size, it sat at the right moment in the rock, and it lay in a seabed of exactly the wrong chemistry. By then, the evidence was piling up from every direction. The global spread of the iridium and the little glass beads, the shocked minerals, the worldwide layer of fern spores marking a scorched and reseeding land. In 2010, a panel of dozens of scientists from a range of fields reviewed all of it together and declared, as plainly as science ever declares anything, that the case was closed. The impact at Chicxulub had triggered the extinction. A few years later, they went and touched the thing directly, drilling from a small platform at sea down into the buried crater and bringing up the shocked granite of its heart, deep rock that had been heaved miles upward and then dropped back as the hole collapsed, exactly as the models of the cratering had predicted. And still, the declaration did not end the argument. Within months of 2010, a number of researchers had published formal objections, arguing that the enormous volcanic eruptions then underway in India deserved more of the blame, and that the field had agreed too quickly, which points to the one part of the story that is still genuinely unfinished. Two questions sit there in different states of unfinished. One is closer to settled than not. For a long time, it was unclear whether the impactor had been an asteroid or a comet, a rocky body from the belt between Mars and Jupiter, or an icy one from the cold outer edge of the solar system, and the difference would say a great deal about how often the Earth can expect such a visit. The answer came, recently, from a chemical fingerprint, a particular blend of metals in the boundary layer that matches a specific kind of asteroid, the dark carbon-rich sort that forms far out beyond Jupiter and matches no comet. The visitor was an asteroid. The other question is more open, and it is the one the dissenters raised. All through the final stretch of the Cretaceous, on the far side of the world, one of the largest volcanic events in the planet's history had been pouring lava across what is now India and loading the air with its own gases. The argument is over how much that mattered, whether it had already weakened the world before the asteroid came, or had largely run its course, or was even jolted into a worse phase by the impact's own shaking. The current weight of evidence puts the asteroid first by a clear margin. The killing tracks the impact, not the lava. But exactly how large a hand the volcanoes had is not a closed question, and honest accounts leave it open. What ought to stay with you from all of this is how recent it is. Every piece of it, the iridium, the crater, the asteroid's chemistry, the shape of the whole cascade, has been worked out inside a single human lifetime, most of it since 1980. For the entire span before that, through every civilization and every earlier generation of scientists, the thin dark line lay in the rock on every continent and said nothing anyone could hear. It took a particular cleverness and a particular run of luck and about 40 years to turn a finger's width of clay into a falling mountain, a darkened world, and the death of 3/4 of life. But all that reading was finally in service of a question that isn't about the dying at all. We have spent a long time now among the dead. It's worth turning at last to the few who didn't die. Because everything alive today, the one telling this and the one listening alike, came down from them. On the afternoon the sky came down, one of the most important animals on Earth was underground and stayed there. It was small, something you could have closed your hand around. Furred, warm-blooded, unremarkable, the kind of creature the great reptiles overhead had never had any reason to notice. It lived in a burrow, as such things did, because a burrow is safe from most of what hunts in daylight. And on this one afternoon, that ordinary habit became the whole difference between a lineage continuing and a lineage ending. Far above its tunnel, the sky was turning to fire as the thrown glass came home. The open ground was cooking, and the unsheltered things, the large and the famous, were dying in the radiant heat. The soil over its back was enough to stop all of it. Down in the dark, the little animal felt the earth above it grow slowly warm, the way ground warms on a hot day. And then, over the following hours, cool again. And it waited, and it lived, knowing nothing of any of it. The pattern is worth sitting with because it runs against everything instinct expects. When we imagine surviving a disaster, we imagine the strong outlasting the weak, the big, the fierce, the dominant, riding it out, while the small things are swept away. A mass extinction does very nearly the opposite. The strong and the dominant are, almost by definition, the specialists, the animals so well fitted to the world, as it was that they had become its kings, the top predator that needs a steady supply of large prey, the giant that needs a forest's worth of leaves a day. When the world as it was ends, those are the first to fall, because their excellence was an excellence at a particular world, and that world is gone. What comes through, again and again, is the unspecialized, the small thing that needs little, the generalist that can eat almost anything, the creature already living at the margins, already spread thin, already used to making do. Catastrophe does not reward greatness. It rewards modesty and a willingness to hide. The burrow that saved the little mammal from the heat saved it again from the cold when the cold came. Underground is a place of few surprises. The deeper you go, the more the temperature settles toward a steady average and stops following the chaos at the surface. While the world above froze through those years of dim sun, a body tucked into the soil, breathing slow, living on stored fat and whatever it could find in the dark, was insulated from the worst of the freezing exactly as it had been insulated from the burning. The same went for anything that could get below the surface, and for anything that could get below the water. A pond, in the months after the sun failed, was a different kind of place from the dying land around it. Its plants were dead or dying, like plants everywhere. But a pond is not fed only by its own plants. Leaves fall into it, and dead wood, and the washed-in remains of things that died on the land nearby, and all of that dead matter is food. Not for animals directly, but for the bacteria and fungi and small scavengers that break it down, which feed slightly larger things, which feed the turtle and the crocodile and the fish. A food chain like that does not run on sunlight. It runs on death, on the steady arrival of dead matter drifting in from the world, and death was the one thing in no short supply. So while the great food webs of the open land and the open sea, the ones built on living, growing, sunlit plants, collapsed from the bottom up, the humble food webs of the ponds and rivers and swamps kept quietly turning. This is why the role of survivors reads so strangely. Turtles came through almost untouched, nearly every kind of them, all the families, straight across the boundary. Crocodiles and their relatives about half lived. The freshwater salamanders and frogs barely registered the catastrophe at all. Strange, water-going reptiles you've never heard of, the Chicxulub, slipped through. In a world that had just lost the dinosaurs and the great sea reptiles, and 3/4 of everything, the dependable winners were pond animals, slow, cold-blooded, unglamorous, plugged into the one kind of food chain the dark could not switch off. Size told the same story as shelter. A large animal is a large appetite. A thing the size of an elephant or a tyrant the size of a bus needs an enormous and constant supply of food simply to keep its body running, and in a world where the food has mostly stopped, being large is a death sentence written out in advance. A small animal needs little, can hide in little, can make do on scraps and seeds and insects and carrion, and can breed quickly enough to replace what the bad years take. None of the survivors were impressive. For a long time afterward, The largest land animals to walk out the far side of the extinction were no bigger than a badger. Everything we would have found magnificent was gone. What inherited the earth was small enough to overlook. Even the one piece of the dinosaurs that survived by these rules. The birds are dinosaurs, the living branch of that vast family. But most kinds of bird died at the boundary too, and the ones that made it tell the same story as everything else. The birds that lived in the trees died when the trees died. Their whole way of life burned and fell with the forest canopy. The ones that came through were ground dwellers and water's edge birds, and many of them carried a tool that turned out to matter enormously, a hard, toothless beak, good for cracking and eating seeds. A seed is a plant's way of waiting out a bad season. A packet of food sealed up and dropped to the ground, able to lie there dormant for years until conditions improve. So in a world with no growing plants, the ground was still scattered with seeds, edible and durable, and the animals built to find and crack them did not starve. The dinosaurs came through in the end as small, ground-running, seed-eating birds. Everything that flies past your window is what was left of them. And somewhere in that company of the small and the sheltered and the seed-eating was your own ancestor. Not a grand one. On the afternoon of the impact, the creature you are descended from was almost certainly something like that first small mammal in its burrow, furred, wary, no larger than a rat, living close to the ground and out of sight, surviving the worst day in the planet's history by being too minor to be in the way of it. Every human being who has ever lived is the descendant of an animal that made it through by hiding. There is no bloodline running back to a mighty survivor, because the mighty did not survive. The line runs back, instead, to something modest enough to fit in a hole in the ground. There is an unexpected comfort in that, if you let it land. The story of the worst catastrophe in the history of animals turns out, in the end, to be less about the death of the great, though the great did die, than about the durability of the humble, the small, the buried, the generalist, the ones already living quietly at the edges, who were spared not because they were strong, but because they had never had far to fall. They came through into a wrecked and silent world, thinned almost to nothing, carrying between them everything that would happen next. And with the dark at last beginning to lift, they started in on the slowest part of the whole story. The long, patient work of making a living world again out of almost nothing. The first green thing the rock records, after the dark, is fern. Just above the boundary layer, that thin line of clay and ash and dust that holds the whole catastrophe, the pollen changes. Below the line, the rock is full of the pollen of a rich and varied world, the dust of countless kinds of flowering plant and tree. At the line, almost all of it stops, and just above it, in layer after layer, there is a flood of one thing, the spores of ferns, and very little else. Pollen counters have a name for it, the fern spike, and it is one of the most legible moments in the entire record because ferns are what come first to ruined ground. They are the plant of the burned hillside and the fresh lava flow and the cleared lot, the opportunist that blows in on the wind, asks little, and covers bare earth quickly, while slower, grander plants are still absent. A spike of fern spores is what a recovering world looks like from below. Not a forest returning, but the first thin green skin spreading over a planet scraped nearly bare. That first green skin took its time arriving, and far longer to become anything more. The fern spike, in the best red places, lasted on the order of 1,000 years. 1,000 years in which the land was fern and little else, the forests gone and not yet replaced, the world holding at the level of moss and weed. That is already a strange interval to sit with. 1,000 years is most of recorded human history, near enough, and at the boundary it is merely the opening pause, the time the planet spent as a fern field before the real rebuilding had even begun. some things came back faster than that. The chemistry of the air, the carbon balance the impact had thrown into chaos, reset within a few thousand years, quickly as these things go, because air mixes fast. But the air is the easy part. Living things keep their own clocks, and theirs run slow. You can watch one of those clocks tick in a place called Corral Bluffs in Colorado, where the rock holds an almost unbroken record of the first million years after the impact, layer by layer, with the animals and the plants caught in it as it went. At the bottom, just above the boundary, the mammals are tiny, the rat-sized survivors, the ones that fit in a burrow. 100,000 years on, there are mammals the size of a raccoon. By 300,000 years, something the size of a beaver. By around 700,000 years, there are mammals weighing 100 pounds and more, the size of a big dog, perhaps 100 times the mass of the little survivors they had descended from. And the rock shows why. The size of the animals tracks the recovery of the plants, step for step. As the forests came back and grew richer, as new and more nourishing kinds of plant appeared, among them the legumes, the bean family, packing protein into their seeds. The animals that ate them had the fuel to grow larger, and they did, in time with the green. Life did not simply switch back on. It was rebuilt slowly, from the bottom of the food chain upward, the same order in which it had come apart, only now running forward and across a far longer stretch of time. The sea was slower still. Down in the water, where the whole base of the food web, the drifting sunlit plankton, had been gutted, recovery ran on a scale that makes the land look hasty. The ocean's great engine, the slow rain of life from the bright surface down into the deep, the thing that moves carbon through the whole system, did not work properly again for something like 2 million years. And the full richness of ocean life, the old diversity of plankton, the variety of shape and size and habit that had taken ages to build and was erased in a few, did not truly return for more than 4 million years after the impact. The sea kept its function and its diversity on 2 separate clocks, and both of them ran in the millions. Set those numbers against a human measure, and they stopped being numbers at all. Our own kind, anatomically modern humans, has existed for something like 300,000 years. All of us, every people and every age, the whole of what we'd call human time. At Corral Bluffs, 300,000 years is the interval between a beaver-sized mammal and a slightly larger one. A single tick of the recovery clock, one rung on a ladder with many rungs still above it. The 700,000 years it took the mammals merely to get large again is more than twice the age of our entire species. The 4 million years it took the sea to fill back up is more than 10 times that. We did not live through the recovery. We are something that happened during it, near the end. There is a particular feeling that comes from holding numbers like these, and it's worth naming because it is the feeling this whole story is really about. It is not fear, and it is not awe exactly. It is something quieter. The sense of a clock running underneath your own, much slower and much larger, that has been running the whole time and will go on running long after. The impact itself, the part with the fire and the wave and the falling sky, took an afternoon. The recovery took millions of years. And the recovery is the truer measure of what happened, because the speed of a wound tells you very little, while the length of the healing tells you everything. A planet that needs 4 million years to refill its oceans has been hurt in a way no afternoon can express. The long winter is the cold that follows the largest things. The long recovery is the silence that follows the winter, and it is far longer than the cold. This is not a comforting thought, and it isn't meant to be. The planet did recover. That much is true, and it is the reason you are here. But recover is doing quiet, enormous work in that sentence. It does not mean the dead came back. They did not. It does not mean the world was restored to what it had been. It was not ever. It means only that life, somewhere in its smallest and most stubborn corners, held on and was given enough time, more time than any human measure is built to hold, to become various and full again in new forms around the shape of what was lost. The reassurance people sometimes take from this, that life always bounces back, is true only on a scale that offers no comfort at all to anything alive at the time. The bounce takes longer than your species has existed. What the story actually offers is not reassurance. It is perspective. The knowledge that you are sitting right now inside one of those long recoveries. That the calm world around you is the far, quiet end of a healing that began in a fern field 66 million years ago, and that the planet's patience, which is the only reason you exist at all, is deeper and slower and stranger than anything a single lifetime is built to feel. And of all the things that happened during that long recovery, among the new forms growing up around the shape of the lost world, one line matters more to us than any other, because it is ours. The small, hidden, hand-sized survivors did not stay small and hidden. Given the millions of years and the emptied world, they spread into everything the dead had left behind and became, in time, almost unrecognizable. And one slender thread of them, after a very long while, became us. 66 million years is a number nobody can really feel. A line is easier, and the whole of this story can be stood up as a single line, because a line is something the mind can almost walk along. At one end of it, 66 million years back, is the small animal in the burrow. Furred, frightened, no bigger than your hand, waiting out the worst day the planet has ever had. At the other end, tonight, is you, lying in a quiet room, warm, listening to a voice. Between those two ends runs an unbroken chain of living things, parent to child, to child to child, every single link of which survived long enough to make the next. The chain never breaks. It cannot ever have broken, because you are here, and the only way to get here is along it. So the small animal in the burrow is not merely like your ancestor. It is your ancestor, the actual creature, one of a small and lucky few, from which the whole line that ends, for now in you, descends. What that line did in the millions of years after the burrow is the great second act of the story, and it happened only because the first act had cleared the stage. For 150 million years, mammals had lived alongside the dinosaurs as small, nocturnal, marginal things, kept little and kept hidden by a world full of larger animals that held every advantage. The impact took those larger animals away in an afternoon and left the world's work, all the ways of making a living that the dinosaurs and the great reptiles had monopolized, suddenly vacant. And the small survivors, freed at last from the things that had pressed them down, did what life does when it is handed an empty world. They spread into all of it. The descendants of hand-sized burrowers became in time the running grazers and the great cats, the burrowing moles and the gliding bats, the elephants, the whales that returned to the sea and grew larger than any dinosaur had ever been. Nearly every mammal you can name, every furred and warm-blooded thing alive today, is a branch off that one radiation, the great fanning out of forms that followed the clearing of the world. None of it could have happened with the dinosaurs still in the way. It is not too much to say that you are walking around inside the aftermath. Somewhere in the early branching of that radiation, a line split off that would, very much later, lead to us, the primates, the group that took to the trees and kept hands and forward-facing eyes and large, hungry brains. And here, the honest version of the story has to slow down and mark a real uncertainty, because the question of when that branch first appeared is genuinely open. Read the rock, and the first creatures anyone is confident to place on the primate line show up just after the boundary, in the early recovery, products of the new and emptied world. Read the molecules instead. Count the slow accumulation of differences in the DNA of living mammals and run the clock backward. And some of those branchings appear to fall earlier in the last stretch of the Cretaceous, which would mean the deepest roots of our own group were already present, tiny and hidden, while the dinosaurs still walked. The two kinds of evidence don't fully agree, and the disagreement isn't settled. The likeliest reconciliation is that both are partly right, that the thread was there, very thin, before the impact, and that what the impact did was not to create it, but to release it, to turn a hidden twig into a flowering branch. Either way, the shape of the thing is the same. We did not arrive in spite of the catastrophe, we arrived because of it. There is something worth doing with that line, slowly, before we leave it. Begin at your own end of it, you, here now, and walk backward. Your parents, their parents, the few hundred generations back to people who left no writing, the longer reach to people who were not quite modern, back through things that walked upright but would not have looked like you, and then things that did not walk upright at all and lived in trees. Back and back, through forms you would never pick out of a forest as kin. And every one of them, every single one across all those millions of years, was born and lived and had young and died having passed the line along. Not one of them failed. Through ice ages and droughts and famines and 100 smaller close calls, the line held, unbroken, every link a life that worked out just well enough. And it runs back, past all of them, to a frightened, furred thing in a hole in the ground on the afternoon the sky fell that happened to be too small and too sheltered to die. That animal does not know you, but you are the reason it mattered, and it is the reason you are here, and on a long enough view, the distance between you is not really very large, and you are its current end, not its purpose. The line was never aimed at you or at anything. It simply kept going, and you are how far it has gotten so far. The body you're lying in right now is the latest shape that small survivor has taken. 66 million years of unbroken inheritance folded into a warm thing in a dark room, breathing slowly, getting sleepy. Everything that animal was, the smallness that saved it, the wariness, the warm blood, the old habit of sheltering in the dark, is in you still, worn down and built over, but never thrown away, because a line like this never starts fresh. It only ever adds. In the way a line of inheritance actually works, you are less the descendant of that survivor than the survivor itself, still going. So here, at the near end of the longest line you will ever belong to, the whole story arrives where it has quietly been heading the entire time. Not at the crater or the winter or the count of the dead, but at a single small, warm animal, awake a little later than it should be, in a quiet room, near the end of a long night. The line has carried 66 million years to reach this. It's worth taking a moment before it does the last thing left to do, to say plainly what all of it amounts to and what it doesn't. It amounts, in the end, to 10 seconds. The whole of it, the falling mountain, the winter, the long dying, the longer healing, the line that runs from a frightened animal in a hole all the way to you, here now. All of it turns on a single stretch of time you could have counted on the fingers of one hand. And the strange gift of having followed the thing the whole way through is that those 10 seconds, which began this as the most violent moment in the planet's history, can be held now without flinching. You can even run the count backward and watch the violence undo itself and find calm waiting on the far side of it. 10. The glass still rising off a finished crater. 5. 4. The ground still tearing open. 1. The half-second of contact, a mountain meeting the sea. 0. The dark old asteroid touching down. And before 0, a point of light too faint to notice, a warm and ordinary afternoon, a shallow sea over a sleeping continent, and a planet keeping its slow time underneath, as it had for 4 billion years and would for billions more. Under all that violence, there was always a floor of calm, and the floor was always there. It is the floor you are lying on tonight. That is the first thing the science can say now, and it can say it with real confidence. The whole chain is visible, link by link, from the asteroid to the ancestor. 40 years of patient work turned a finger's width of clay into a sequence you can walk without skipping a step. The motion that became heat, the heat that became vapor, the vapor that became a rain of glass around the world, the glass that became a burning sky, the burning sky that became a winter, the winter that became a long silence, and the silence that became, very slowly, a different living world. By the time you reach the end of it, the catastrophe has stopped looking like an accident and started looking like physics, like the only thing that could have happened, given a mountain falling that fast onto that one unlucky patch of sea. Nothing in it was magic. Every step followed from the step before. That is the deepest thing the long study of this has brought us. Not the drama, which we could always imagine, but the inevitability, which we had to earn. And then there is the second thing the science can say, which is harder and more honest, how much it still does not know. The broad shape is settled, the edges are not. We do not know, even now, how much of the world actually burned in those first hours, or whether the fires were global or only scattered. We do not know exactly what closed the sky, whether the dark was mostly soot, or mostly the impact's own fine dust, or the sulfur of that drowned seabed, or some shifting mixture of all three. We do not know how much the great eruptions in India, going on at the same time on the other side of the world, added to the dying, though the weight of the evidence now puts the asteroid first. We are not even certain whether the dinosaurs were flourishing or already thinning when it came, or precisely when our own deep ancestors first branched away. None of these gaps threatens the story. The story holds. But it is worth sitting with how much remains genuinely open about the most closely studied catastrophe in the planet's history. Because if this much is still uncertain about the one event we have looked at hardest, it is a fair caution about how much we are ever truly sure of. The honest posture at the edge of all this evidence is not triumph. It is a careful kind of humility, looking steadily at what is known and what is not, and refusing to pretend the second pile is smaller than it is. There is one more thing worth saying about the present, and it has to be said carefully because it is not a warning and not a lesson. It is only a fact, and a strange one. The same physics that ran that day runs every day at every size. Small pieces of rock fall onto the earth constantly. Most are dust and burn up as the shooting stars we began with. Now and then, something larger comes. A little over a century ago, a rock perhaps 50 meters across came down over Siberia and flattened 2,000 square kilometers of forest with a blast in the air. About a decade ago, a smaller one, the width of a house, exploded over a Russian city and broke windows for miles, filmed by 1,000 car cameras on the way to work. These are the small ones, the kind the atmosphere can still mostly handle, the kind that burst in the air rather than reaching the ground for exactly the reason the big one didn't. There is enough air to stop a house. There was never going to be enough to stop a mountain. And here is the strange part, the one that would have been unimaginable through almost the whole of the story we've followed. The line that began with an animal hiding in a burrow has, in the last blink of time, produced something that looks up. We have found the old crater and read it. We have catalogued nearly all of the large asteroids whose paths cross our own, and confirmed that none of the big ones is coming anytime soon. And a few years ago, we did a thing no living creature on this planet had ever been able to do in 4 billion years. We sent a small craft out to a harmless asteroid, struck it on purpose, and measured, afterward, that we had nudged it onto a slightly different path. It was a tiny push to a tiny rock a long way off. but it means that the descendants of the survivors are for the first time not entirely at the mercy of the sky. The animal in the burrow could only hide. The thing it became can watch and understand, and just barely, just lately, reach back. All of that, though, the looking up and the reaching back, is only the last instant of a story that is mostly about patience. Set the present down again and go back to the long middle, the part with no people in it at all, the millions of years after the impact, when the world was simply slowly putting itself back together, with no one watching and no one to reassure. That is the long quiet the whole event finally comes to rest in. The fires were out within a year, the winter within a few, but the quiet lasted in its way for ages. Forests grew back where there had been fern fields. The small survivors fanned out into strange new shapes and filled the empty world. The oceans, slowest of all, took millions of years to grow rich again, the plankton rebuilding their countless kinds in water that had nearly gone sterile. None of it was dramatic. There was no moment of triumph, no morning when the planet announced that it had recovered. There was only the steady, patient, unwatched work of life doing what life does when it is given enough time, which is to continue and to branch and to slowly make more of itself until a wrecked world was a living world again, and almost nothing was left to show how close the whole thing had come to ending. And the world you live in is the far, calm end of that. The weather outside the window, the birds in the morning, the particular green of growing things, all of it sits at the quiet end of the longest recovery in the planet's recent history, so far downstream of the catastrophe that nothing about an ordinary day carries any mark of it. You are alive in one of the calm stretches. Most of the planet's long biography has been gentler than its worst days suggest, and this is one of the gentle parts, and you are in it. Here, then, is the whole of it, the thing underneath the physics and the numbers, the reason a story like this is worth telling quietly at the end of a long day. The planet keeps a kind of time that human beings are not built to feel. A time in which an afternoon of fire and 66 million years of healing are both simply events, both held in the same slow patience, neither one hurried and neither one final. We are very new to that time. Our entire species is younger than the recovery from a single one of the planet's bad days. And there is a particular calm available in knowing that, not the cheap calm of being told everything will be fine because the planet promises nothing of the kind, and the dead of that long extinction were never made whole. The calm is harder and truer than that. It is the calm of scale, of understanding that you belong to something very old and very patient that has been broken before and has always given enough time gone on, and that the same depth of time that swallowed the dinosaurs is the depth you are floating in right now, holding you exactly as gently as it held them. You do not have to do anything with that. You only have to feel for a moment how large and how unhurried the thing is that you are a small living part of. The 10 seconds were never really the point. The patience underneath them was. So there is nothing left to learn tonight, and nothing left to fear. The hard part of the story is long over 66 million years before you were born. What is left is only the quiet and the dark and you in it. And the dark is worth one last thought, because it is, in a way, the same dark. The long winter was a darkness that fell over the whole world and did not lift for years, and it did most of the killing. The dark in your room tonight is its small, tamed descendant, a darkness that falls every evening and lifts every morning, that you have never once had to fear. That means only that the planet has turned its face from the sun for a few hours and will turn it back. The same planet, the same turning, only gentled by all that time into something you can sleep inside. You are very small and the night is very old, and neither of those is a frightening thing. The animal you came from survived its long dark by going still and waiting. You can do the same. There is nothing coming. The sky is quiet and watched and almost empty. The mountain fell a long, long time ago, and everything it was ever going to do, it has already done. And what it left behind in the end was you. Awake a little longer than you need to be, warm, breathing slow, at the far, calm end of the longest night the world has ever had. So let the count go. Let the 10 seconds settle back down into the deep time they came out of. There is nothing to hold on to now, and nothing to watch for. The mountain is down, the winter is over, the planet is patient, and it has all the time there is. And tonight, so do you. Rest now.